All right. So, last section of the year today. All right. In your notes, I want you to put these four things down. Okay. So, we're going to title this event or this lesson the probability of a compound event. The word compound, what does it mean? Multiple. Could be two. Could be essentially more than one. Okay. We've done compound inequalities where we had an inequality statement that had two inequalities in it at the same time. Today, we're going to look at the probability of a compound event, and it's going to fall into one of two categories. So, first thing we're going to look at is the difference between what it means to be independent versus dependent, which is different than when you're looking at like X values and Y values, inputs and outputs. Those are also known as independence and dependence. All right. But when you're talking about events, we're going to talk about that. What's your feeling or your thought on the word independent events? What do you think that means? Independent events. Alone, okay. Singular, yeah. What else? So the fact that you guys over here on this side of the room are having your own time, which is great. You want people to listen to you, but the moment it goes away from you, now you're screwing around. So thank you for that. You want to start that over because I know they didn't hear you, and neither did I. Okay. All right. In order to be independent, what does that mean? Are any of you independent? Well, you have to be on your own, right? Dependent means what? You need something else. You're impacted by something else. All right. You're affected by something that happens. There's more. Okay. So when we start this idea of independence versus dependence, do the events impact each other? If they do, that's dependent because one of them is causing a direct impact on the other. If they're independent of each other, they completely can stand alone. Okay. And then we're going to get into the idea of what it means to be mutually exclusive or not. This one's a little bit harder. I don't, because you're not really going to pull it out of these words, I don't think. Anybody know what it means to be mutually exclusive? You want to take a guess? That's okay. What do you think? Okay. So to affect both in a good way, is that what you said? Okay. All right. Okay. We're gonna let that one go. We're not. All right. So we're really looking at four ideas today. We're going to start with independence, then into dependence, then mutually exclusive, and then not. And so that's why you see these four things over here. We're going to talk about how do we find each one of those here at the beginning. So we'll let this go from yesterday. Um, Independence versus dependence first. That's where your homework kind of starts, and then into this idea of mutually exclusive. So two events that can both occur at the same time that do not have an impact on each other are considered independent. All right. There is a key word in there when we talk about the probability of these two events happening, and we say A and B. Okay. We're going to find that by taking the probability of A and multiplying it by the probability of B. And you'll see that here in a second about how these two events are going to stand alone. Okay. Their two things are going to go off without impacting or affecting each other. Well, it's right here. Okay, so right, that's the piece right there that you want to put in for the statement of an independent. Compound events, that's what we're looking at today, meaning more than one. So here we're talking about having event A and event B, so just two different things, and then we multiply those results together. So it may look something like this. Okay. So how many of you have been on an airplane before? How many of you that have been on an airplane have had a connecting flight to another one? Has that flight ever been delayed? What can impact that delay? Weather's one of the biggest things to impact the delay of a flight, right? Where? Okay, clear.
They are terrible. And like one of the engines like went out and they were like, we have to send in a rescue plane or whatever.
Oh,
And
all right.
the rescue
It's aggressive.
AC wasn't working. So we were at the airport for
Hey,
12
it's
hours.
cheap for a reason.
Yeah.
Okay.
We're not doing that again.
All right. Now, if you read this one here, okay, Ray is on a flight from Birmingham, that's in Alabama, to Chicago, and it's got a flight record of being on time 90% of the time. So that's pretty good. On the same day, the chances of it raining in Denver are 50%. Whether the weather in Denver, is it going to have any impact on a flight from Alabama to Illinois? So that's why they're independent of each other. Okay. If you were flying from here to Florida, let's say, what is the airport that most of you will have to go through on your way from here to Florida? Do you know? No.
Tennessee?
No.
Somewhere in there.
Okay, so it's Atlanta is your big hub that is typically going to lead into that direction. So if there's weather in Atlanta and I'm flying from here to Florida, there's a very good possibility that one's going to impact the other. But in this situation, those two things are not going to impact each other. They're nowhere near each other. So to find the probability of the flight being on time and there will be rain in Denver, and that's a big word when you're talking independence versus dependence, the fact that both of them are going to take place, we're going to multiply those results together. Okay? So, well, here's what we got to look at first. What is the probability that her flight's going to be on time? So there's a 90% chance that flight's going to be on time. The second thing that we need to look at is it going to rain in Denver? Well, what's the probability that it rains in Denver? 50%. So I'm taking those two things. The probability of the first one, so 90% we can think of as 9 out of 10. The chance of it raining, that's the second one. We can think about that as 5 out of 10. And we are going to multiply those two results together to find the probability that both of them happen. How do you multiply fractions? Straight across. Okay, so multiply straight across. So 45 out of 100, which is, we are not about to, 45%, right? It's out of 100, right? 45%. Okay, so two events taking place. We want to know the chances that both of them are going to happen. All right, so try this one and see what you come up with for an answer. Hopefully, it matches one of those percentages at the bottom. Jack, you got a name tag on today?
No, I voted for Flash Fiction.
Oh.
Mr. Jason's class, we all wrote Flash Fiction, so we put them up, and we had to vote which one was the best.
Got it.
And then we demanded a voting system.
Ooh, demanded.
Yeah, so he hand wrote every single person in the class.
He had stickers?
No, just tell him my tape.
Got it. My apologies.
Index card of the tape.
Got it. No, it's clear. It's the beauty of it.
It's like clear tape.
Hey, watch it.
You can see clear tape when people put it in front of the pictures on their posters. For like projects and stuff.
Okay. What you got? C? How'd you come up with that? Okay. So the fact that they lie on different fault lines and there's a 60% chance and a 40% chance, I take those two percentages, multiply them together, okay, and get my result. And again, it's two things here. Number one, there's a 60% chance of the first one, and secondly, there's a 40% chance of the second one, and we want to know the probability that it's going to happen in both places. I have a typo in there. You see it?
What?
I have a typo in there.
Oh.
2020.
Yeah. Yeah. I have 2024 in both of these and not there. Got it.
Yeah. No solution.
No solution. Impossible. All right. So yes, in this situation, you have a 6 out of 10 chance and a 4 out of 10 chance. So you're looking at 24 out of 100. So yes, that would be 24%. Okay. So independent events. Now, that in conjunction with the idea of a dependent event is a little bit different. So in my second one, we're going to put this statement in its place. All right. So the probability of A and B will be the probability of A being multiplied by the probability of B. It says following A. Oftentimes I won't say following A, I usually say after A. All right. Now, dependence means that one of them is affecting the other. Okay. So let's do it right now. I'm going to give you an opportunity to not have to take your final exam.
Wait,
Yeah.
actually?
Okay.
Mr. Johnson always made these bets.
We're gonna have to take it.
So here's the deal. All you got to do is pick a card. Like literally, give a name.
Oh,
Name me a card. The Queen of Hearts. So we'll just make sure that the Queen of Hearts is in here. Okay, because we don't want you believing that you're being cheated. All right. Well, maybe this. Oh, there it is. Queen of Hearts. All right. Everybody sees it. So it is real. All right. So all you have to do, pull the Queen of Hearts. If you pull the Queen of Hearts, you don't have to take the exam.
Don't we have to take the?
No, well, obviously, only one person can win this, like the COVID vaccine free 4-year college. Did you see that? Yeah, give me a full 4 years for free, right? They are. Yeah, so 5 different people. Okay. That's a cool trick right there. If that was the Queen of Hearts, I'd quit. Oh, Queen of Spades. All right. So that'd have been next level stuff right there. If I would have done that, I was walking out the door. All right. So here's the deal. If you want a chance to do this, all you have to be able to do is tell me your chance of winning. Okay. And then you can pull. You'd like to try? You don't have any cards in the deck. That's problematic. There's no jokers in here. 1 out of what? 52. So here you go. Remember, you're looking for the Queen of Hearts. Anywhere you want. Everybody always likes to pull out of the middle. Oh my Lord, take one.
I wanted.
Oh my goodness. Jeez. So 5 of spades. 5 of spades. You want in? You gotta be able to tell me though. What are your chances of winning? You know what it is?
Yeah, because isn't there 51? No, there's 4.
But he took
a card out because.
52
minus
Yeah.
1
is 51.
I know that. I know there's 51 cards, but then
you don't
there's
have it
4
anymore.
spades in there.
Well, hold on now. He's looking for
The
you.
Queen of Hearts.
You only have one. Yeah, you got to pull the Queen of Hearts.
So 1 out of 51.
So 1 out of 51. Take that one right there.
No.
Oh,
What if it's
could have been it. Oh my goodness gracious, girl. Oh, Jack of Hearts. Should have took that one. How many? 1 out of 50. What is it? 9 of clubs. Not clover. You know, when we play cards and the clovers, that was the clover. What do y'all got your hands up for? Well, of course you do, right? Okay. Now, in this situation, this is considered a dependent event. Well, maybe it changes, good or bad, as each person goes, right? Good as long as what?
you're taking stuff away?
Good as long as what? As long as you don't pull the card, right? Because Logan's opportunity was 1 out of what? 52. Olivia, yours was 1 out of 51.
Oh my God.
Quinn's was 1 out of 50. And it continues to get a little bit better as long as somebody doesn't pull it. The moment that card gets pulled, if it gets pulled, then everybody after that point, it's a 0. Because there was only one, and the one is gone. Now what?
Wait.
Okay. What?
Has anybody gotten it?
Not today. No.
Did you
Okay.
actually tell them that they didn't have to go final?
Well, what do you
But
mean?
they went after the ace of spades. So when we say the probability of B following A, what we're saying is B's results have been impacted by A's results. And in this particular case, it was because when Logan pulled a card, what did he not do? Or what did I not allow him to do? Well, no. Put it back. The fact that he kept the card is what created the dependent event. Okay? So if we use words like keep, not replace, not put back, or maybe it's something that can't be putting back. Can't be put back. Okay? Can you think of a situation where once it happens, it's happened? There's no,
Crash into a car.
oh,
Bite a donut.
A flower.
Isn't it like you can't put the toothpaste back?
okay, yeah,
It's
once,
just
yeah,
walking by
once that's out.
Sport.
What do you mean?
Like say you bet and then they pass the mark.
Okay,
You can't go
once it's
back.
over, it's over. All right.
when you shave an eyebrow.
Yeah, when you decide to cut your own hair, there ain't no putbacks after that. All right. Now, take a look at this. This is like the best school carnival prize wheel you're ever gonna get. Look at a. You get a hairbrush, some sunglasses, keychain. I mean, what else you want? All right. What else you want? Now, based off of this, what the question and here's the piece right there, and maybe and not replaced, not putting it back. Once you get it, it's yours. Very similar to the cafeteria line prior to COVID rules. But you would watch people go through the cafeteria line, take something, and then get to the next item and decide they'd rather have the next item and put the first one back. That's gross, right? Once you take, you got. No take backs, no give backs, maybe. Okay. What are the chances here, though, that the first thing that's pulled is a pair of sunglasses? I don't agree that it's one. How many sunglasses are in the 4 out of 15? So in terms of the sunglasses, there's a 4 out of 15 chance that that's the first thing taken. Now, what are the chances that we get a hairbrush? 6 out of 14. Because why?
No. 4
'Cause-
sunglasses. He's asking hairbrush.
Okay, hold on. Because it says that 3 prizes are randomly drawn. So now, if this question was sunglasses and then sunglasses again, now it's 3 out of what? If this next one is a sunglasses, then it's 3 out of 14. But in this case, because hairbrushes are a different category, it's now 6 out of 14 because I've taken one away. And at this point now I've taken 2 away. So in the last case, keychains is 5 out of 13. Okay. So 5 out of 13. Now, what do I do with those 3 fractions? You multiply them together. Okay. And so if I multiply those together, what do I get? Andrew, what do you got? 4 over 91. Okay. Now remember, we multiply fractions straight across, so you could 4 times 6 times 5, 120 over 15, 14. That's big. I don't know. But ultimately, it's going to reduce down to 4 out of 91. So you have a 4 out of 91 chance that if we randomly take 3 things out of there, What are the chances we get one of each is essentially what we're asking, right? What are the chances we get one of, you got a 4 out of 91 chance that that's going to happen. Right. You don't have a very good chance, right? Just like you didn't have a very good chance of pulling the card, right? I mean, would I have to figure out a way to eat it if you decided to pull that one card? Yeah, because if I told you that's what's going to happen and you did it, but I'm going to bank on the fact that you're not going to do it. You know what I'm saying? And then secondly, absolutely, as I continue to let you do it, what happens? The chances get better and better and better. So as a person who can't really stand in front of you and say, hey, if you randomly take this card and you get it, then I'm not going to make you take your final, even though everybody else has to take their final. I can't let that go too long. And yes, 1 out of 52 is a pretty slim margin, right? I mean, 1 out of 50. Oh, sure, and it could, right? Well, actually, one time it did happen.
And did they not have to take their money?
At that point, I think the bet was something different, but I did pay it up because I did offer it as and it
Would you
it
ask,
happened.
like,
Kind of like made my heart hurt a little bit when I saw it. Like, oh my goodness, I can't believe that just happened. But it can though, right? I mean, it is possible. So you got to be careful, right? But I mean, a 1 out of 50 chance, which is what I think Quinn had. 1 out of 50 is 2%. Right? I mean, if you double 1 out of 50, you get 2 out of 100. So not a very good chance that it's going to happen. But if I continue to do it enough times, it's going to start to improve the chances. It's eventually going to happen to me.
how do we get out of doing our final? Like, could you totally get us out of doing it?
No, you're on. All right, try this one, and then we're going to move to the other side of exclusive and not. Now here, I would argue that we probably don't even need the phrase "it is not replaced." I'm kind of uncertain how you might get a gumball back into the machine. You know what I mean? So even in that situation, even without the words, I think we're going to have to believe this is a dependent event. Like, I don't see, yeah, you're like, no, I do not want the white gumball. Back into the hopper you go. I want a new one. You could buy another one, right? You could buy one. Like, that would do it for you, but you can't make that undo the process. That's why they do that little whirly spin on the way down, so you get to watch the pain of the wrong gumball coming all the way down the chute. You know what I mean? You're just like, oh, the whole way down. What are you gonna do?
They last for like 2 minutes anyways.
Yeah, on a good day. Okay, so the question is, what are the chances I get a red, a green, and a blue? And remember, She got jokes. All right. I'm multiplying these results together. So essentially what I'm asking is, what are the chances I get one of each? That's really what I'm saying here. And because, again, the word used in this problem right here, what are it contains red ones, blue ones, and green ones. Find the probability of each of these happening. You should have 3 probabilities listed. What's the probability of getting a red one?
16 out of 44.
16 out of 44? Okay. What's the probability of getting a green one? What is it? 10? No. Okay. Out of 43. Okay. And yes.
How are you getting from like 44 to 40?
Well, right, because once a gumball came out, at the beginning, the 16 red gumballs, there were 44 in the hopper. One of them came out. I'm down a gumball. I no longer have 44. I now have 43 in there. So as the second one comes out, I'm now down 2 gumballs. So I know this last one's got to be something out of 42, because the gumball can't go back. Quinn, what's up?
Wait, how did you go from 16 to 40?
Well, because the color changed. So red was the first one, so that's why it was 16. Then green was the next one, and green is 18. So who told me 10?
Yeah, that's what I did.
So this number is not a 10. Hi, Riley.
Which one were you talking about?
Oh, you don't get to turn around and play the
Oh, I
blame
thought you
game.
said blue gumball.
Then the last one is blue,
Sorry.
and blue is 10. So that is, now in this case you would,
It's 10
It-
out of over 40.
hey, no reason to yell.
And like, but you're
You're multiplying. And in fractions, in true, you multiply straight across. So it would not impact the result. You're right. But if we're going to try to make sure we understand what it is we're doing, we better make sure we have them correct. What's up? Okay. What do you got? Okay. Uh-huh. What are you telling me with that? Am I supposed to do something with it?
Wait, see, that's what popped up on mine too.
Okay. So there's my numerator, right? 28, 80. That's 16, 18, and 10. And then 44, 43, and 42. Wow, that's big. 79,464. Okay. So first and foremost, I don't see that answer over here. So I either got to try to reduce. What are you thinking, Trevor? This one here. What did you do to figure that out? You did what? You were able to reduce that fraction over there? Okay. I did not. What? Why are you yelling at me?
I wasn't yelling.
Yeah.
I was gonna say,
Yeah, you were. It's all
I
right.
don't know if it's A. Because
B is the correct answer.
I kept dividing up them by 2.
Uh-huh. And you could do that. Continue to divide them by 2. I'll be honest with you. Listen, my mind. I thought, there's a fraction. I'm going to use the ABC button. I'm going to reduce it. It turned it into a decimal when I did that. Okay. So I got 2 choices. I can, because these are even numbers, start cutting them in half and try to bring them down that way. Okay. Full disclosure with you, I did not do that. I went to these 4 choices and did well with them.
Divided them.
I turned them into decimals,
Yeah.
and I found the 2 decimals that matched each other.
I just divided those 2 numbers and then I got a decimal and then I turned that into a fraction.
Okay. And that fraction turned out to be this fraction. There you go. Okay. So sometimes if we're looking at our first result and it doesn't line up, that cannot be my indication to stop. I'm not problem solve. Figure out something to get you through that's going to get you to where you need to be. Okay. So independence versus dependence. Is every one of these events free of each other, independent? They don't impact. Or are my subsequent events impacted by my previous events? Namely, am I keeping it? Am I not replacing it? Am I not putting it back? Something that would indicate to me that I'm affecting those results. Okay? Now, here's the other side of things. Mutually exclusive means both things that you're talking about can't be true. All right? So here's an example. If you look at the one at the bottom, a card is being drawn from a deck. Find the probability of a 7 or an 8. There is no card in the deck that is both a 7 and an 8. You with me there?
No.
Do you know any cards in a deck that are a 7 and an 8 at the same time?
They're like separate.
Correct. Now, when you look at independence versus dependence, it's the probability of A and B. When you look at mutually exclusive or not, look at the word or. So in this situation here, the probability of A happening or the probability of B happening, a 7 or an 8. Now, I don't multiply those probabilities together. I add. How many 7s are in a deck of cards? How many 8s are in a deck of cards? What are the chances I get a 7 or an 8? 8 out of 52. Okay, so I take those probabilities and I add them together. Okay, so if you cannot read the purple statement there, it is this one right here that you want to put in your notes. We want to add those 2 things together. Okay, so here, a card is drawn. Find the probability that it's neither a club nor a heart. how many clovers, let's call them.
Is it called a club?
Yes, it's called a club. How many clubs are there in the deck? You guys have no clue about cards. 13.
Yes, poker, that's real.
Okay.
Wait, I'm pretty.
So let's back up 1 second. You have a heart, a diamond, a club, and a spade. Those are your 4 cards. If there's 52 total cards in a deck, if you divide 52 by 4, you get 13, which means there are 13 of each of them.
Yeah.
So there are 13 clubs. There are also 13 hearts. So what's the probability that you don't get a heart or a club? It would be half of that. Add those together. 26 over 52. No? Where did I lose you?
Okay, what the
Go.
No, not the common denominators. It's like the deck of cards.
Uh-huh.
Because don't you have, if it's neither club nor heart, it's
Right.
like 8 of those? Since there's like 4 and 4.
No. There's not 4. There are 13 clubs, there are 13 hearts, there's 13 diamonds, there's 13 spades. There are 4 sets, or suits as they're called, but there's 13 of each of them, from an ace to a king. Now, if you go cross suits, yes, there are 4 of each number, so there's 4 aces, 4 twos, 4 threes. But again, you're still talking about having 13 things, and if you have 4 of each of them, 4 times 13 is 52, so you're still getting that 52. All right. You guys, you just don't play with cards enough. I mean, most of you, I would assume.
Clearly.
Yeah, you keep saying that. Okay. Good. All right. So, what's the probability that a member is chosen from random as a junior or a senior? Okay. A junior or a senior. Those are mutually exclusive. You cannot be a junior and a senior at the same time. That is not possible. So you should be coming up with 2 fractions. What's the probability of being a junior? Getting a junior out of this group of French club kids? What's the probability of getting a senior? And then at this point, I would be adding those 2 together.
Wait,
What?
okay. So,
I'm waiting and holding on.
hold
I'm still holding. Let me know when you want me to be done holding.
Yeah, hold on. Just 1 second.
All right.
Okay, so it's out of so combine the juniors and the seniors makes 37.
Okay, but hold on now. You're talking the French club has 16, 12, 15, and 21 kids. So you need them all.
I need them all.
You need them all. That's going to, so your total.
But when I do like 16 over 64.
Okay. So,
What would my number be next?
okay. Well, this was juniors, right?
Yes.
As far as seniors are concerned, oh, that's wrong. If this is juniors, this number's not 16. It would be 12. Okay, so 12 out of 64. Now over here, we're not. This isn't like pull one, keep them. The question is, what are the chances that I get a junior or a senior? So it's still out of 64, and then this number would be 16. Now your denominators match. Okay, so we can add that together. So we end up with 28 out of 64. Now that's not one of my choices, but if I reduce it, I get 7 out of 16.
Couldn't you just add 12 and 16 and get your 28 and
Uh-huh. Yep. But when I shortcut things, you often tell me I need to hold on or wait, or you don't have a clue, or you don't. So if I'll put it in pieces, then we can get to that point. You know what I'm saying? All right. Now, last one.
What are you wearing?
Baseball shirt.
Thanks.
What is that?
You're being recorded right now.
I think this is mine.
It is yours.
I didn't tell them to
Hey,
put
guys.
this back.
Now, last one. If things are not mutually exclusive, meaning that it's possible that they have occurred in both situations. Meaning, if I'm gonna, if I'm gonna take, what are the chances that I get a boy when I pull the, let's say, all right, here's where I'm trying to go. It's okay. When you said juniors and seniors, there was no way you were going to get an overlapping kid because juniors and seniors don't cross paths. Okay. But let's say I took the speech and debate team and I took the science club. Is it possible that there could be somebody who's on the speech and debate team and is also in the science club? Okay. So even though I said it's an or idea, somebody from here or there, it's possible that there's the same somebody in both of those scenarios. And essentially what I've done is I've counted them twice. I counted them in the speech and debate group, and I also counted them in the science club group, which was not a concern when we talked about juniors or seniors because they don't overlap with each other. Are you with me there? So when we talk about things being not mutually exclusive, okay, then we're starting the same way. What's the probability of A or B? And I will continue to do the beginning part the same. Find the first probability, add it to the second probability. But now you're going to have to take out anything that got hit twice because you've overcounted. Okay, so that's what this last part down here is saying. Right here, this, you got to minus anybody that would have got hit twice because you've double counted them. Could be. All right. So we're going to look at two examples here. Yeah. Now, you know anybody that plays bingo? Man, do not mess with somebody in their bingo. Don't be touching their daughters. Don't be touching their cards. Right? Oh my goodness gracious. They don't play. All right. Now, the question here says, what's the probability that I get a multiple of 5 or something from the end column? That or right there is my kicker for this being either mutually exclusive or not. Now, the reason this falls into the not category is because it's possible to get a multiple of 5 that's also in the end column. Like if you know how the game of bingo works, right? You get your card, but there's only certain numbers in the B column, and there's only certain numbers in the I column, the N, the G, and the O. Okay? You with me on that?
Yeah.
All right. So in this first column, you can only have the numbers 1 through 15, but there are multiples of 5 in that column. How many are there in that column?
3.
There's 3, right? 5, 10, and 15. Now in the I column, how many are there? 3, right? It would be 20, 25, and 30. In the N column, in the G, and in the O. So a grand total of how many multiples of 5?
A lot.
15, right? So there are 15 out of how many? 75, okay? Now, what are the chances I get a multiple of 5? That's 15 out of 75. Or, so that's why we add something from the N column. Well, how many numbers are in the N column? Numbers in the N column is 15. From 31 to 45 is 15. So that's 15 out of 75. But because I can get a multiple of 5 that's also in the N column, how many of those are there? 3. I've actually counted them twice. So I've got to take out 3 of those that I put in. Okay. The numbers 35, 40, and 45 would have gotten counted here, and they would have gotten counted here. Do you follow me on that? So for that reason, I have to take them out. Now, some of you may be thinking, well, couldn't I just take them out of one of these numbers along the way? And absolutely, that's true, right? And say, well, I counted them in this one, so I'm not going to count them in the second one. That's fine. In fact, you're still completing this fraction here. You just aren't writing it as a third option, but you're still completing it. Or you write out all three parts. Now, because the denominators are the same, okay, you can keep the denominator. 15, 15, and a minus 3 is 27. Okay. Now, 27 divided by 75, I can reduce that to 9 out of 25. Okay. So you have a 9 out of 25 chance of getting a multiple of 15 or something from the n column. All right. Independence versus dependence. What's the word that you need to identify? Independence and dependence. And if it's mutually exclusive or not, the word is or. You need the word or. Okay? So that paper in front of you is the last homework assignment of the year.